Hi children, today continue the chapter electrochemistry. Children, in the last class we had discussed about the redox reaction, electrochemical cell, galvanic cell, and how the cell reactions which are taking place in the galvanic cells are represented. That is the representation of the galvanic cell. So in the representation of electrochemical cell, the anode reactions are represented on the left hand side, the cathodic reactions are represented on the right hand side, and these two reactions are separated by the two vertical lines that represents that the anodic reaction and cathodic reaction, that is the one half cell and the another half cells, are separated by a U-shaped salt bridge. So children, today we discuss about the next topic of the chapter, that is the electrode potential. So how can we define the electrode potential? What do you mean by the electrode potential? So when a strip of metal, that is the capital M, here this is the picture regarding this is the metal strip having the metal M. When this metal strip is brought in contact with the solution containing its own ion, that is the Mn+, that is the ion which is formed by this metal. So when a strip of metal is brought in contact with the solution of its own ion, then three possible processes can take place. The first process is, this metal ion may collide with the metal strip and bounce back without any chemical change. Here this metal ion may strike with this metal strip and it bounce back without undergoing any chemical change. Then second condition is that this metal ion may collide with the strip and gain N electrons and get converted into the metal ion, that is the ions are reduced. Here this metal ion, here the reduction is taking place. This is the reduction reaction. The metal ion in the solution, this metal ion may collide with the metal strip, and here in the metal strip it may gain the N electron, and after gaining the N electron, this metal ion undergoing the reduction reaction, and this reaction can be the reduction reaction can be represented as, that is the metal ion after gaining the N electron, it converted into the metal atom. The third possible process that can take place in this, that is the metal atom on the strip, this is the metal atom on the strip, may lose the N electron, and after losing the N electron it enter into the solution in the form of Mn positive ion, that is it undergo the oxidation reaction. And the oxidation reaction can be written as, that is the metal atom which is present in the strip may lose its N electron, and after losing its N electron, this metal atom is converted into Mn+ ion. So these are the three important processes that may take place when a strip of metal is brought in contact with the solution containing its own ion. Next is the development of positive charge on the metal strip. How the positive and negative charge are developed on the metal strip. This is the picture regarding the development of negative charge on the metal strip. This is the development of negative charge on metal strip. Okay, so in this we can see that this negative charge develop on the metal strip only if the metal has relatively high tendency to get oxidized. The positive charge is developed on the metal only when the metal has high tendency to get oxidized. That is the metal having high tendency to get oxidized. This is the condition only when there is possibility to develop the negative charge on the metal strip. Now, if the metal has relatively high tendency to get oxidized, its atom would start losing the electron, because in the case of oxidation reaction, the atoms are losing its electron, and when the atom loses its electron, it changes into the ions, and after that it passes into the solution. The reaction may possibly take place as that is this the metal, and this is the metal on the metal atom on the strip. This metal atom is present in the strip. So in the equilibrium condition, what happens? This metal converted into Mn positive ion, and after converting into the ions form, it passes into the solution, and after passing into the solution, it also loses by converting into the metal ion, that is all, it also loses the N electrons. Okay, so when the metal has high tendency to get oxidized, the metal atom start losing the electron, and it changes into the positive ions and pass into the solution. The electron lost, here this is the picture, the electron lost get accumulated in the metal strip and cause to develop the negative charge on the metal strip, and when it develops the negative charge on the metal strip, it does not allow the metal atom to continue losing the electron, because there is an equilibrium is attained, but it would, since here a negative charge is developed on the metal strip, so it would try to re-attract the metal atoms from metal ions from the solution, and to neutralize its charges. So ultimately a state of this equilibrium is attained between the metal atom which is present in the strip and the ions which are present in the solution at the interface. So again I would like to explain this. Students, the development of negative and positive charges takes place on the metal strip. So development of negative charge takes place only if the metal has relatively high tendency to get oxidized. So when the metal has relatively high tendency to get oxidized, its atom would start losing the electron and changes into the positive ion, and after converting into the positive ion, it passes into the solution. So the electron lost, it accumulated inside the metal strip and causes to develop the negative charge on the metal strip. The negative charge which when developed on the metal strip does not allow the metal atom to continue losing the electron when the equilibrium is attained, but it would re-attract the metal ions from the solution in an order to neutralize the charge, and ultimately after some time a state of equilibrium will be established between the metal atom which is present in the strip and the ions at the interface. Next is the development of positive charge on the metal strip. How the positive charge are developed on the metal strip. Similarly, in the development of positive charge on the metal strip, the metal ions has greater tendency to get reduced. Here the metal has greater tendency to reduce. Only when the metal has greater tendency to undergo the reduction process, then only the positive charge is developed on the metal strip. Whereas in the case of the development of negative charge on the metal strip, the metal has greater tendency to undergo the oxidation process. So here the development of positive charge on the metal strip, if the metal ion has relatively high tendency to get reduced, they will accept here the metal ion from the solution come in contact with the metal strip, and they accept the electron from the metal strip, and consequently it converted into the metal atom, and when they converted into the metal atom, there is a net positive charge is developed on the metal strip, and ultimately a state of equilibrium is established between the metal ions and the metal atom at the interface. So what is the chemical reactions involved in this? That is the metal ion from the solution from the solution accept the electron, an electron from the metal strip and undergo the reduction process to convert it into the metal M. Okay, and when it converted into the metal M, there is a positive ions are formed inside the metal strip, because the metal M is converted into the Mn positive ion by losing the electron, and the loose electron were gained by the ions which are present in the solution, and after that ultimately a net positive charge is developed on the metal strip, and in this way the metal strip develop the positive charge. So in these three conditions and the development of negative and positive charge, in either case the separation of charges at the equilibrium state results in the electrical potential difference between the metal and the solution of its own ion. When a potential difference is existing between the metal and the solution of its own ion, that is known as the electrode potential. Okay, so the exact potential difference at the equilibrium, then what are the important factors on which the electrode potential depends of a metal? So the electrode potential of the metals depends on, at the equilibrium, depends on the nature of metal. So the first is depends on the nature of metal, concentration of ions, temperature. Then depends upon the nature of metals or ions, concentration of ions and the temperature. These are the important factors which determine the exact potential difference at the equilibrium, and these are the important factors on which the electrode potential of a metal depends. Okay, after that children, there are next important term, that is the how the half reactions are represented according to the IUPAC convention. So according to the present IUPAC convention, the half reactions are always written as the reduction half cell. Here it is very important to note you that the half reactions in the case of electrochemical cell, the half reactions are always written as the reduction half cell, and their potential are represented by the reduction potential, not the oxidation potential. Here it may be noted that there are some points regarding this. The first is reduction potential means the tendency to gain electrons, and oxidation potential means the tendency to lose electron of an electrode are numerically equal but have opposite sign. Reduction potential increases with increase in the concentration of ions and decreases with decrease in the concentration of ions in the solution. The reduction potential of electrode when the concentration of ions in the solution is 1 mole per liter and the temperature is 298 Kelvin is called standard reduction potential. It is very important, that is the standard condition for an electrochemical cell is that when the concentration of ions in the solution is 1 mole per liter and the temperature is 298 Kelvin. This is the case when the components are existing in the solution form, and it is represented as the E naught reduction, or simply we can write as the standard electrode potential, that is the E naught. This naught represents the standard condition of the electrochemical cell. In the case of gaseous electrode, what is the standard condition? In case of gas electrode, the standard condition chosen are 1 bar pressure and 298 Kelvin along with 1 molar concentration of ions in the solution. Fourth point is the absolute value of E naught, that is the standard electrode potential. E naught is the standard electrode potential, cannot be determined because once the equilibrium is reached between the electrode and the solution in a half cell, no further displacement of charges can occur unless and until it is connected to another half cell with different electrode potential. This difficulty is overcome by finding the electrode potential of various electrodes relative to some reference electrode whose electrode potential is arbitrarily fixed. So students, to select a electrode potential whose value is to select a standard electrode, reference electrode whose electrode potential is fixed, the common reference electrode used for this purpose is standard hydrogen electrode, that is represented as the capital SHE, whose electrode potential is arbitrarily taken to be 0. After the electrode potential, next topic is the cell potential or EMF of the cell. The cell potential, or EMF of cell. EMF means the electromotive force. Electromotive force. Okay, so first, what do you mean by the term the cell potential or EMF of the cell? So in the case of electrochemical cell, the electrochemical cell consists of two half cell. One is the oxidation half cell and another one is the reduction half cell. The electrode in these half cells have different electrode potential. So when the circuit is completed, the loss of electron is taking place at that electrode having the lower reduction potential. That is, the electrode having lower reduction potential undergo the oxidation. The loss of electron taking place at that electrode having the lower reduction potential, whereas the electrode having the higher reduction potential undergo the reduction process because it has greater tendency to accept the electron. So the gaining of electron occurs at that electrode having the higher reduction potential, whereas the loss of electron is taking place at that electrode having the lower reduction potential. So in this case, in the case of electrochemical cell, the two half cells having the different electrode potential, so the exact difference in the electrode potential of two electrode of the cell is termed as the electromotive force or E cell voltage. So the difference in reduction potential of two half cell in a cell is called EMF, electromotive force, or cell voltage. It is also named as the cell voltage, which is represented as the E cell. Okay, so the difference in the electrode potential, reduction potential or electrode potential, we can write the electrode potential or reduction potential. So the difference in the electrode potential of two half cell electrodes in a cell is called the EMF or the cell voltage or E cell. So mathematically, how can we express the electromotive force or cell voltage of a electrochemical cell? So mathematically we can write as, that is the EMF, electromotive force, is equal to, that is the electromotive force is the difference in the electrode potential of the two half cell which are present in the electrochemical cell. That is the EMF is equal to E reduction, and the reduction is taking place on the cathode, minus E oxidation, and the oxidation is taking place on the anode. So mathematically we can write the EMF, and that EMF is also E cell. E cell is equal to E cathode minus E anode. that is the reduction is taking place on the cathode electrode and oxidation is taking place on the anode electrode. So the EMF or the cell voltage E cell can be mathematically expressed as, that is the EMF is equal to E reduction minus E oxidation. But students, in the case of representation of the galvanic cell, the anodic reactions are written on the left hand side, whereas the cathodic reactions are written on the right hand side. So the EMF can also be written as, that is the E cell or EMF, that is may also equal to, that is the E cathode. The cathode is present on the right hand side, that is the E right minus E left. That is the electrode potential which is present in the right hand side of the half cell and electrode potential which is present in the left hand side of the half cell. So it is simple form ER minus EL. So in this way we can mathematically express the electrode potential or electromotive force of the electrochemical cell. So after that we come on the definition of the electromotive force. So the electromotive force of a cell is defined as the potential difference between the two terminals of the cell when either no current is drawn from it. Here one important point is noted that for any type of electrochemical cell, the value of the cell potential, the value of the cell voltage or the electromotive force is always in positive sign. That is the E cell is always comes in a positive value. This is very important. So students, this I like to explain this with the help of an example, that is a cell reaction, and in this cell reaction the copper and silver ions are taking place. So first I would like to explain this with the help of an example, that is the copper solid plus Ag plus ion undergo the reaction to form, undergo the redox reaction to form, the copper is converted into copper plus 2 ion and the silver is converted into the silver metal. Okay, here the copper is in the solid form, this Ag plus is in the aqueous form. After that, in this reaction, this copper solid is converted into the copper plus 2 ion and that copper plus 2 ion passes into the aqueous solution. It means here the copper is converted into the copper plus 2, that is the oxidation. It undergo the oxidation reaction and the oxidation reaction is taking place on the anode. Okay, and here the Ag plus is converted into the Ag. It means it undergo the reduction and the reduction is taking place, this is taking place at the anode and the reduction is taking place at the cathode. Okay, so now after that, after clear this, the reduction and oxidation, we can separate the anode oxidation half cell reaction and cathode reduction half cell reaction. So the anode oxidation half cell reaction can be written as, what is the reaction which is taking place at the anode, the oxidation half cell, that is the copper solid. After losing its 2 electron, it converted into the copper plus 2 ion and it passes into the aqueous solution by losing the 2 electron. Okay, similarly the cathode, on cathode reduction reaction is taking place. So the reduction half cell reaction can be written as, that is, here what reaction is taking place, that is the Ag plus 2Ag plus gain the 2 electron which is lost by the copper and here the Ag plus is present in the aqueous solution and after that it converted into the Ag solid. So this is the anode and the anode oxidation half cell reaction is taking place, and at the cathode, cathodic reaction is on the cathode, reduction reaction is taking place. So students, the sum of these two half cell reaction gives the overall cell reaction. In this, the copper electrode is acting as a anode, whereas the silver electrode is acting as a cathode. So how can we basically represent this cell? How can we represent this cell? So this cell can be represented by using the same representation in the case of galvanic cell, that is the anodic reactions are written on the left hand side and cathodic reactions are written on the right hand side. So here the anodic reaction is cell representation, the copper is converted into copper plus 2 in the aqueous, and this is the solid. Two vertical lines, these two vertical lines represents that the two half cells are separated by the salt bridge, and here the Ag plus aqueous is converted into the Ag solid. This is the representation of the cell. So in this case, we can simply calculate the electromotive force or the E cell for this cell by using the formula. That is, the formula is the E cell is equal to E right minus E left. Okay, E right minus E left. Then how can we write the E right minus E left? Basically the electrode potentials are written as the reduction potential. So the E right, E cell is equal to, E right means on the right hand side this reaction is taking place. So we can write the E reduction of Ag plus 2 Ag minus E left, that is this reaction, that is the copper plus 2 is converted into copper. Okay students, so in this way, for any type of electrochemical cell, we can calculate the electromotive force or cell voltage of a cell, and we can here the E right minus E left, or we can write that is the E cell is equal to E cathode minus E anode. This is the basic formula to calculate the E cell voltage or EMF of the electrochemical cell, and the EMF of a cell is defined as the potential difference between the two terminals of the cell when either no current is drawn from it. And one important point, notice that the E cell means cell voltage or electromotive force is always in a positive sign value. So this is a reaction which is given. So in this reaction the copper undergo the oxidation reaction. So when students you are provided with any type of electrochemical cell reaction, so with the help of the cell reaction you can easily identify which species is undergoing the oxidation reaction and which species is undergoing the reduction reaction. And so by identifying the oxidation and reduction reaction, we can easily predict that which element is acting as an anode, which reaction is taking place at the anode, and which reaction is taking place at the cathode. So in this, the copper is converted into copper plus 2, Ag plus is converted into Ag. This is oxidation and this is reduction. So after that we can separate these reactions as a oxidation half cell and reduction half cell. This is the combined chemical reaction which are redox reaction which are taking place in that electrochemical cell. So here the copper is converted into copper plus 2, and by losing 2 electron, this is the oxidation half cell reaction that is taking place at the anode. On the cathode, the reduction half cell reaction is taking place, that is a 2 Ag plus gain the 2 electron to convert it into the silver. So by using the formula, that is the E cell, the E cell is equal to E right minus E left. The electrode potential is basically represented as the reduction potential. So here the right is Ag plus 2 Ag reduction reaction, and left may E is equal to copper plus 2 copper. So we can write as the E cell is equal to E cathode minus E anode. After that, the next topic is the measurement of electrode potential. So students, the potential of individual half cell cannot be measured. We can measure only the potential difference between the two half cell, that gives the value of EMF of the cell. That is, the EMF or E cell of a cell can only be calculated by knowing the value of the electrode potential of the two half cell. But if the arbitrarily choose the potential of one electrode, then we can determine the potential of another half cell. So in order to determine the potential of half cells, a half cell called the standard hydrogen electrode, that is the SHE. That SHE is used to determine the electrode potential of the half cell. So children, today we discuss the electrode potential, the EMF or electromotive force or the cell voltage. So children, in the next class we continue this by starting the standard hydrogen electrode. Till then children, be safe and keep learning.